Hi. In this video, we are going to continue the section on inequalities that we are doing, and we are going to talk about the rearrangement inequality. So let me state the inequality here. Let two groups of numbers, A1, A2, AN, and B1 to B2 till Bn satisfy the following inequalities. A1 is less than equal to A2 is less than so on till less than equal to AN. And similarly, B1 is less than B2 less than Bn. Then we can show, then we have A1 times Bn plus A2 times Bn minus 1 and so on till An times B1 is basically less than equal to A1 Bt1 plus A1 Bt2 plus An Btn, and that is less than equal to A1 B1 plus A2 B2 plus AN BN. Now here T1 T2 till Tn is a random permutation of the set 1 to n, of the sequence of numbers 1 to n. So what is the meaning here? Think about it. A1 multiplied by Bn, A2 multiplied by Bn minus 1. So this is the product of the terms of these two sequences taken in the reverse order sum, right? So you are taking terms, the smallest term here and the largest term here, and you are multiplying, and then the second smallest and the second largest. And similarly, you are constructing this sum of pairs taken from two different sequences. The only quality about this particular sum is that it's a reverse order sum. The minimum and the maximum are being multiplied. This sum is basically a random order sum, because T1, T2 till Tn is a random permutation of 1 to n. So we don't know A1, B, T1. T1 could be the term 5 or T2 could be term 6. Tn could be the first term. We don't know the order, but it's a random order sum. We are taking pairs from the two different sequences as before, but this time we don't care about the order. So the first inequality here says that the reverse order sum is less than equal to a random order sum. And finally, the biggest possible sum that you can create here is the same order sum. What is this? Here you are multiplying the smallest element with the smallest element, A1 and B1, A2 and B2. So these are the second smallest elements. And similarly, the highest element is multiplied with the highest element. So the logic of the inequality should be pretty obvious, because think about it, if you have a sequence of numbers, if you want to construct sums like this, let's take two sequences, 1, 3, 5, and another one is 2, 4, 6, right? So if I want to construct a sum like these, and I want to create the smallest possible sum, I should create 1 into 2, 3 into 4, 5 into 6, right? This is the largest possible sum. My mistake. Why? Because this plus this plus this, when you are multiplying the largest elements from each of these sequences, the magnitude is enhanced a lot, right? So here it is 30 plus 12 plus 2, which is basically 44, whereas the smallest possible sum would be the reverse order sum. Reverse order sum would be 1 into 6 plus 3 into 4 plus 2 into 5, right? Correct. So this will be simply 6 plus 12 plus 10. So that is 28. So the smallest possible one is when 1 is multiplied with the biggest one, 3 is multiplied with this, 5 is multiplied with this. And the largest sum that you could make is when you multiply the small ones together and the larger ones together, right? So the idea of the inequality is pretty simple. And the key idea is that same order sum is always greater than a random order sum. And that is greater than the reverse order sum. When you have two lists of numbers in a particular order, you can always use this logic and rearrange the numbers to form different sums and inequalities. Now, what we'll do is we'll learn how to apply this in problems. So let's look at the first question here. Question 1 says, assume that A is greater than 0, B is greater than 0, C is greater than 0. We have to prove that 1 by A plus 1 by B plus 1 by C is less than equal to A power 8 plus B power 8 plus C power 8 by A cube, B cube, C cube. Okay. So they have not told us the order of A, B, C. So without loss of generality, we can assume that A is greater than equal to B is greater than equal to C is greater than 0. So we are assuming this here. So then obviously from here it follows that A square is greater than B square is greater than equal to C square. And it follows then that 1 by C cube will be greater than 1 by B cube is greater than 1 by A cube. Why? Because when we write it like this, A cube is greater than B cube is greater than C cube. We take reciprocals, it will become 1 by A cube. We'll have to change the inequality sign. It will become like this, right? Similarly, what we can also say is we know from here 1 by A is less than equal to 1 by B is less than equal to 1 by C. So therefore, it follows from this that 1 by BC will be greater than equal to 1 by CA is greater than equal to 1 by AB, right? Why are we getting this? We are taking two different sequences, or you can just think about it. 1 by BC is the product of the two largest terms, and 1 by AB is the product of the two smallest terms. And the middle term is the 1 by CA, which is the smallest and the largest, right? Correct. So this is obvious. We have these sequences ready for us, and we'll use these somehow to figure out how to prove this problem, right? Okay, so let's try to think about 1 by A plus 1 by B plus 1 by C. And you can think of it as A square times 1 by A cube plus B square times 1 by B cube plus C square times 1 by C cube, right? So we have two sequences, A square, B square, C square, and 1 by A cube, 1 by B cube, 1 by C cube, right? Okay. So A square into 1 by A cube is the reverse order sum, if you think about it. This is reverse order sum of these two sequences, because A square is the largest term and 1 by A cube is the smallest term. So you're multiplying largest and smallest. This is a reverse order sum. So that should be less than equal to the same order sum, right? That should be less than equal to A square, which is the largest, multiplied by 1 by C cube, which is the largest here, plus B square by A cube plus C square by B cube, right? So what we have gotten so far is 1 by A plus 1 by B plus 1 by C is less than equal to A square by C cube plus B square by A cube plus C square by B cube. How did we get here? We got it by applying rearrangement inequality one time. Reverse order sum is less than equal to same order sum, right? Let's see what we can do from here. So I'll do it on the next screen. We have 1 by A plus 1 by B plus 1 by C less than equal to A square by C cube plus B square by A cube plus C square by B cube. And we can write this as equal to A power 5 by a cube c cube plus b power 5 by b cube a cube plus c power 5 by c cube b cube, right? Now think of the two separate sequences, a power 5, which is obviously greater than equal to b power 5 and c power 5. And we also have the sequence 1 by AB is less than equal to 1 by CA is less than equal to 1 by BC. So we have 1 by A cube B cube is less than equal to 1 by C cube A cube less than equal to 1 by B cube C cube, right? We have these two sequences which are true. And now think of what kind of a sum is this? This is A power 5, the largest term, multiplied by A cube C cube, right? The middle term. And similarly, B power 5 multiplied by the smallest term. The middle term is the smallest term, right? So this is looking like a random order sum, right? Random order sum that is being constructed from these two sequences of numbers. It is not the same order sum because then you would have to multiply a power 5, the largest one here, with b cube c cube, right? So a random order sum will always be less than the same order sum. So a power 5 multiplied by 1 by b cube c cube plus b power 5 multiplied by c cube a cube plus c power 5 multiplied by a cube b cube, right? So we have this, and now this thing, if you take LCM, this is equal to a cube b cube c cube, and this becomes a power 8 plus b power 8 plus c power 8, right? So now we have established our inequality that we desired, right? We have 1 by a plus 1 by b plus 1 by c is less than equal to this, right? We have done it by applying twice the rearrangement inequality, right? One step was when we established the fact that 1 by a plus 1 by b plus 1 by c is less than equal to a square by c cube plus b square by a cube plus c square by b cube. And then we rewrote it like this here and applied rearrangement again after changing the terms to a power 5 and a cube and all, right? So two applications of rearrangement inequality have helped us prove this one. Okay, let's go on to the next question. Let's look at this one. Question number 2. Here we have, suppose x is greater than y is greater than z is greater than 0. We have to prove that x square y by z plus y square z by x plus z square x by y is greater than equal to x square plus y square plus z square. Okay, let's think about this one. So we have x is greater than y greater than z. So we can say that since x is greater than equal to y is greater than equal to z, x square is greater than equal to xy, and that will be greater than equal to y square, right? What have I done? I have taken x greater than y, multiplied it with x, x square is greater than xy comes from here. And similarly, I have taken y is greater than equal to y and multiplied it with x here and with y here. Because x is greater than y, xy is greater than y square, right? So we have that x square is greater than xy is greater than equal to y square. And in the exact same manner, we can also show that z square is less than equal to yz less than equal to y square. Exactly same method, right? Okay. Now we have two different sequences. Let's think of what we can claim by doing rearrangement inequality here and construct two different sums, right? So if you do reverse order sum, that will be less than equal to the same order sum, right? What is the reverse order sum? This is the largest term here, and this is the smallest term here. You multiply those to construct the reverse order sum. So x square z square plus xy into y square plus y square into yz. Actually, Right now I have not made the reverse order sum because I have multiplied y square into yz, the middle term here, and xy into y square, right? So this is not a reverse order sum, this is a random order sum, random order. And that is less than equal to x square into y square, the largest terms, plus xy into yz, and the smallest term y square into z square, right? This is the same order sum. Here the order is a little mixed, but it is not reverse order sum. We have a random order sum here, which is less than equal to the same order sum, right? So we have this inequality, and here we can say from this that x square z square plus this is xy cube and this is y cube z. We can take y cube common, it is x plus z is less than equal to, on the other side we have x square y square plus y square z square plus y square xz. So actually we can say y square common, x square plus xz plus z square, right? This is the inequality that we have so far. So I will just simplify this on the next screen. I have so far x square z square plus y cube x plus z is less than equal to y square x square plus xz plus z square, right? And simplifying this by taking x square z square on the other side, I can write y cube x plus z is less than equal to y square x square plus xz plus z square minus x square z square, right? Okay. Now we know from the problem that x is greater than equal to y is greater than equal to z is greater than 0. So therefore x minus z by y is positive. X minus z by y is positive. I want to multiply by x minus z because that will make this x square minus z square and this one x cube minus z cube. So I want that x minus z somehow, right? So I will multiply both sides by x minus z by y. So multiplied by y cube x plus z is less than equal to y square into x minus z by y multiplied by x square plus z square plus xz minus x square z square multiplied by x minus z by y. Right, let's see what happens here. Y cancels once, it becomes y square, x square minus z square is less than equal to y times x cube minus z cube. And here you get minus x minus z x square z square by y, right? Okay, so simplifying these terms, we get x square y square minus y square z square is less than equal to x cube y minus yz cube. And here we have two separate terms. We have x cube z square by y and plus x square z cube by y, right? Okay, I will collect some of these terms on the other side. I will bring this and I'll bring this on the other side and I'll bring this here, right? So I'll write it like x square y square plus yz cube plus x cube z square by y is less than equal to, we have y square z square plus x cube y plus x square z cube by y, right? Okay. This is what we have gotten so far. So if I divide both sides by xz, what happens? So dividing by xz, both sides, I want to construct a term like x square y by z. Why am I trying to divide by xz? Because in the desired inequality, I have terms like x square y by z and y square z by x and so on. And seeing what happens here, if I divide by xz, I will get x y square by z, right? Plus xz here. So this becomes y z square by x plus xz here to become x square z by y is less than equal to, dividing by xz here, I get a y square z by x plus x square y by z plus x z square by y, right? Correct. So I have this inequality that I have gotten so far, right? So what I can say, I'll just write it on the next screen. The inequality we have obtained so far is x y square by z plus y z square by x plus x square z by y is less than equal to y square z by x plus x square y by z plus x z square by y, right? So therefore, I can say that the square of this x square y by z square y by z plus y square z by x plus x z square by y whole square. Notice that this is the square of the RHS. RHS square will be greater than, I can write one term as the LHS z square y by x plus y square x by z, and one term as the RHS itself, which is x square y by z plus y square z by x plus z square x by y. So what am I saying here? This is the RHS here and this is the LHS, right? This inequality is true. RHS was bigger than LHS. So therefore RHS square should be greater than LHS into RHS, right? So this is a true inequality. And now what I want to do is I want to say that this product of these two is greater than equal to x square plus y square plus z square whole square. Because ultimately I want to prove this is greater than this, right? Okay, so how do we do that? Notice that this term and this term are nice and symmetrical by applying Cauchy's inequality on the vectors. I want to prove that this is mod A whole square mod B whole square is greater than A dot B whole square, right? So for this to be mod A whole square, the terms of my A vector are what? Is x root over z by y plus z root over y by x and y root over x by z. And my B vector can be x root over y by z, and I can take the second term as this one. So it is z root over x by y, and the third term is this one, which is y root over z by x. So clearly, this into this is basically mod A mod B whole square. And now what is the dot product of A dot B? Dot product of A dot B is this dot this. So that is simply x square plus y square, x square plus z square plus y square. So whole square, right? So this step comes by Cauchy's inequality. Cauchy's inequality says that this product of x square z by y, z square y by x, y square x by z with x square y by z plus y square z by x plus z square x by y is greater than x square plus y square plus z square whole square, right? So therefore, we have RHS square is greater than this square. So therefore, we have shown that x square y by z plus y square z by x plus x z square by y is greater than equal to x square plus y square plus z square. So think about this. While solving this question, we did not use rearrangement inequality so much. We actually used at the end Cauchy's inequality, and we just did a little bit of simplification. There was nothing major to it above and beyond the simplifications that we did, right? Let's see another question. This is the third one. Let there be two groups of ordered numbers a1 less than equal to a2 less than equal to an, and b1 less than equal to b2 less than equal to bn be given. We have two sets of ordered numbers as above, and we have to prove that 1 by n a1 bn plus similarly till an b1, which is like 1 by n times the reverse order sum, right, is less than equal to a1 plus a2 plus an by n multiplied by b1 plus b2 plus bn by n, and that is less than equal to 1 by n of a1 b1 plus a2 b2 plus an bn. So think about it. This is the same order sum, right? Same order sum, because here you are multiplying the smallest terms with each other. The smallest terms and the largest terms are multiplied together, and this is the reverse order sum, right? So the first and third inequalities are automatically true by rearrangement inequality, right? So that is not an issue for us. However, we still have to prove the middle term here, right? And actually, this is called Chebyshev's inequality. So we are going to supply a proof of Chebyshev's, and we are going to use the rearrangement inequality to do it, right? Okay. So now let's try and think how we are going to do this. So what I will do first of all is write the reverse order sum here, a1 bn plus a2 b of n minus 1, so on till an b1. We know that this is less than equal to a1 b1 plus a2 b2, which is the same order sum, plus an bn. This is a simple statement of rearrangement inequality, right? Now what we do here is we multiply, we add it, we write another rearrangement here. We say that a1 bn plus a2 bn minus 1 and so on till an bn1 is also less than equal to, this is a slightly different arrangement, a1 b2 plus a2 b3 plus an minus 1 bn plus an b1, right? So think about what I have written here. This is the reverse sum. This is also the reverse sum. These two are identical LHSs, right? This is the same order sum, and this is almost the same order sum, but shifted by one element. So a1 is not multiplied with b1, but with b2. And similarly, a2 is multiplied with b3, and an is multiplied with bn, right? b1. So I keep writing this sort of inequalities. On the left side, I'm always keeping the reverse order sum, right? We know that the reverse order sum is the smallest possible sum of all the possible permutations of sums that you could construct like this, right? So here I will write now a1 b3 plus a2 b4 and so on till an b2. And I will continue writing these till I get a1 bn here plus a2 bn minus 1 plus an b1 is less than equal to, this time it will be a1 bn, right? We are coming to the equality case here. We are writing the reverse order product here, reverse order sum completely here, right? Actually, the last inequality is an equality rather than an inequality. I have started by the same order sum and I have then shifted the terms one by one step at a time basically, right? If you add up all of these inequalities, what I would get is n times a1 bn plus a2 bn minus 1, so on till an b1 is less than equal to, when you add it, add these vertically, okay? So you'll get a1 and now you'll get b1 plus b2 till bn plus a2, and now you should get here b2. Okay, I feel like I have missed a row here. A2, if it is A1 BN, it should be A2 B1, right? Correct. I have I have not written this last row correctly here. I will just write it. So what should happen is, this side is the reverse order sum, and this side is, you started from A1 B1 A2 A1 B2 till A1 BN. So here you will get B2 B3 B4, BN would have come in the previous row and you would have gotten A2 B1, right? And so on till the end. Here you should get an and you should get b of n minus 1, right? Yeah, that is the correct order. Now you add all of these vertically and you will realize that here a1 common b1 plus b2 till bn, and here a2 common b1 plus b2, and bn would have come somewhere here in the previous row, right? So we are able to write it like this. And finally, an common, you start with bn plus b1 and so on to on, we reach till bn minus 1, right? So this is less than equal to, this is clearly b1 plus b2 plus bn common, and we get a1 plus a2 till an, right? So you are getting n times a1 bn plus a2 bn minus 1 plus an b1 is less than equal to this. And now dividing by n square on both sides, I can write the inequality that I desired. I write a1 bn plus a2 bn minus 1 plus an b1 divided by n is less than equal to a1 plus a2 plus an by n multiplied by b1 plus b2 plus bn by n. So we have proved Chebyshev's inequality here, which is saying that the average value of the reverse order sum is less than equal to the product of averages of the two sequences, right? So this is the reverse order sum divided by n, because there are n terms here. So this is the average value of a term in the reverse order sum is less than equal to the product of the averages of the two sequences, right? And that is less than equal to the average value of the same order sum. This first part of the statement was obvious from rearrangement inequality. We just had to show how to do the middle proof, right? So this is a proof of Chebyshev's using rearrangement, right? Let's look at another problem. Question number 4. We have let xi is greater than 0, where I is going from 1 to n. We have to prove that summation of I goes from 1 to n, 1 by 1 plus xi multiplied by summation of xi, where I goes from 1 to n, is less than equal to summation of 1 by xi power k, I goes from 1 to n, multiplied by summation of I goes from 1 to n, xi power k plus 1 by 1 plus xi. Okay, so here we can assume that without loss of generality, let's assume that x1 is greater than equal to x2 is greater than equal to xn. We have assumed this So that implies that 1 by x1 is less than equal to 1 by x2 less than equal to 1 by xn. Correct. Okay. So once we have this, we can raise it to powers, and raising it to powers basically further reduces these terms. So we can say 1 by x1 power k is less than equal to 1 by x2 power k less than equal to 1 by xn power k, right? We have these, and we also know that if you multiply uh, okay, I want to construct a term like this. So how do I construct that? Let's think about it. We have 1 by 1 plus x1 is less than equal to 1 by 1 plus x2 less than equal to 1 by 1 plus xn. This follows from here, right? And we also have xi, x1 power k is greater than equal to x2 power k greater than equal to xn power k. That comes from here, right? So if we combine these two, right, x1 power k by 1 plus x1. So, right. So think about it. x1 power k by 1 plus x1. Will it be greater than x2 power k by 1 plus x2? We know that 1 plus x1 is greater than equal to 1 plus x2, right? And so on. So when you divide, you will not be certain, right? 1 by 1 plus x1 is less than equal to 1 by 1 plus x2. And let's check whether this is true or not. Here we can check it by cross multiplying and subtracting. x1 power k plus x1 k x2 minus x2 power k minus x1 x2 power k, right? So what we are getting is x1 power k minus x2 power k plus x1 x2 x1 power k minus 1 minus x2 power k minus 1. So it is obvious that this is positive and this is positive, and x1, x2 are both positive. So this is greater than 0. So this inequality is true. I have confirmed it by simply cross multiplying among, right? So what we know now are these facts here. We know, first of all, x1 is greater than x2 is greater than xn. We know 1 by x1 power k is less than equal to 1 by x2 power k less than equal to 1 by xn power k. Third thing is 1 by, we know x1 power k by 1 plus x1 is greater than x2 power k by 1 plus x2 is greater than xn power k by 1 plus xn. We have established these inequalities, right? Okay. So now let's look at the target that we have. We have summation I goes from 1 to n, 1 by 1 plus xi multiplied by summation I goes from 1 to n xi. This is equal to, we can write it as summation of I goes from 1 to n xi multiplied by, I can rewrite this term as 1 by xi power k multiplied by xi power k by 1 plus xi, right? The summation I goes from 1 to 1. The second summation is still the same, but I have multiplied and divided by this just to make use of the information that we know already, right? Okay. Now, notice that this is a reverse order sum, right? Look at the second sequence here and look at the third sequence here. The smallest term of the second sequence is being multiplied by the biggest term of the third sequence, right? So this is a reverse order sum, and Chebyshev's inequality tells us that 1 by n of a reverse order sum a1 bn plus a2 bn minus 1 and so on is less than equal to sum of the a's by n multiplied by sum of the b's by n, right? So I'm going to apply Chebyshev's inequality to these two, considering these as my AIs and these as my BIs, right? So what I can say is less than equal to, so 1 by n is here, and I have just a summation here. So I can multiply this by n here, and I will get simply a 1 by n left over here, right? So this is less than equal to 1 by n summation of xi. I goes from 1 to n is understood. And now I'll do summation of the AIs, right? So this is basically simply summation of I goes from 1 to n 1 by xi power k product with summation of xi power k by 1 plus xi. This is the summation of the BIs, right? These are two separate summations now. That is the point of Chebyshev's. So I have the product of terms here, reverse order sum summation is less than equal to the separate summation of the two separate series, AIs and BIs, right? Great. So let's think about what that means now. So we can write correct 1 by xi power k, and okay, I will just do it on the next screen. I have this right now, right? So I'll take that on the next screen. We have summation of I goes from 1 to n 1 by 1 plus xi multiplied by summation of I goes from 1 to n xi. We said that it is less than equal to 1 by n summation of I goes from 1 to n xi multiplied by summation of I goes from 1 to n 1 by xi power k multiplied by summation of I goes from 1 to n xi power k by 1 plus xi, right? So now we can write this as less than equal to 1 by n summation of I goes from 1 to n 1 by xi power k, and I will introduce a summation I goes from 1 to n xi by n. I have intentionally introduced an xi by n here. So obviously I should multiply by n the remaining term. So xi power k into n by 1 plus xi. I goes from 1 to n. So I have divided by n here and I have multiplied by n here. That doesn't change anything. So I can rewrite this as summation I goes from 1 to n xi power k by 1 plus xi by n, right? And here it is summation I goes from 1 to n xi by n. Okay, correct. And I have here less than equal to 1 by n summation I goes from 1 to n 1 by xi power k. Okay. Now, applying Chebyshev's again, and this time I will apply Chebyshev's to these two series, to these two summations, right? Think about it. I know Chebyshev's inequality says that summation of a1 bn and so on till an b1 by n is less than equal to summation of ai by n summation of bi by n. Now suppose I have two different summations here. This is my summation ai and this is my summation bi. So that is greater than equal to the product of them, right? The product in the reverse order, right? So what we can say is, because we already know that xi power x1 power k by 1 plus x1 is greater than x2 power k by 1 plus x2 and so on. And we also know that x1 by n is less than equal to x2 by n and so on. We can say that the reverse order product of this, right? So reverse order product will be simply x1 power k plus 1 by n times, here actually the term is by n here, n times you get 1 plus x1 by n, right? This is the reverse order product, x2 power k plus 1 by n times 1 plus x2 by n, right? Of these two sequences, that reverse order product by n is less than equal to these two summations separately divided by n square, right? So these two summations separately are greater than basically so what I can write here is less than equal to summation of I goes from 1 to n 1 by x I power k, and you have a 1 by n here, and we can say multiplied by n square by n summation of xi power k plus 1 by 1 plus xi. Because when you multiply, when you use Chebyshev's here, we get xi power k plus 1 by 1 plus xi and a n on top. So that is why I am doing n square by n. So this basically cancels the n here, and you have less than equal to summation of 1 by xi power k and summation of xi power k plus 1 by 1 plus xi. That is what I am getting. The second time that you are applying Chebyshev's is a little tricky. You have to think of rearranging the order of the terms. The first time we applied Chebyshev's, that was not a problem. But here we have to apply Chebyshev's to this and this. And I multiplied and divided by n up and down, right? The reason I did that is only then will you be able to cancel the n's at the end. So here we have xi by n and this term here, and we know the sequence in which they are ordered, right? So the reverse order sum is what will help you get an xi power k plus 1, right? So the question is a little tricky. We are using Chebyshev's, which we had earlier proved by rearrangement. And once you have these two, we can apply Chebyshev's again here and say that it is less than equal to this xi power k plus 1 by 1 plus xi, and outside this term remains as it is. All the n's get nicely cancelled out. So you have to be a little careful here. Go through the steps once more. Hopefully the whole idea of rearrangement inequality should be clear through the problems and all that we have discussed in this video. So that's all for this one. The next class will be basically on convex functions and Jensen's inequality. So that is also a frequently used inequality technique in Olympiad problems. So we'll cover this in the next video. So that is a good place to stop for this video. I'll see you next time.